All right, so we're going to start talking about ratios and proportions, and so we're going to go back through and talk about ratios in some context that if you're in a geometry class you have seen before, and then we're going to add on some new things about ratios that are new or different, or we're kind of expand on some ideas. So let's just go back and start off by reviewing what a proportion is. Sorry, what a ratio is. A ratio is just the comparison of two values, right? So we can compare, in this particular example, the height of two trees. We can compare your speed to time. We can compare the lengths of the sides of a triangle, anything like that. And we're trying to come up with a value that represents a comparison between those two things that we're comparing, right? And so there's a couple of different ways that we can write about ratios, and so one of them is to use fraction notation. So when we talk about fractions, we're really talking about ratios. We're comparing two values, the numerator and the denominator, and so something like that might look like 3 over 4, right? That would be a good way to compare a value of 3 to a value of 4. Or we could write in a different notation, and this is what I have written as A to B notation, which would be, say, 3 to 4, using a colon instead of a fraction. And those are both valid ways of writing them, and we're going to use both of them over the course of our talk about ratios and proportions and similarity. Right? And so let's take a look at this example just to see how to do this comparison. So they're talking in this case about a bonsai bald cypress tree, which is kind of like a mini little tree. And then they're talking about if we compare that to a full-size tree, which in this case they're referring to a senator tree, and they want us to compare these values using a ratio of the height of the bonsai to the height of the senator tree. And so here's the first important thing, is that when we're comparing values using ratios, it's helpful, or in most cases, or important that they be in the same units. So if you notice, the bonsai tree that they're talking about on the right-hand side, this picture is in inches, and when they talk to us about the senator tree, they're talking about it in feet. So the first thing we're going to do is take the senator tree and let's change it into inches. So we're going to do a little bit of what's called unit conversion, or if you've been in a chemistry class, we call it stoichiometry, right? So we're going to talk about 118 feet, okay? And we want to change the feet into inches. So if you know your unit conversions, we know that there are 12 inches in 1 foot. So it's going to be my goal to make it so that the units cancel. So I'm going to put 1 foot on the bottom, and I'm going to put its equivalent form, which in this case is 12 inches, on top. So the reason that I chose to do this is because the anything in the denominator of a fraction and the numerator of a fraction will cancel, so I can cancel out feet and feet, right? And I can say that this is now an inches conversion. So I know that in order to make this conversion, I need to do 118 times 12, which is 1,416 inches. So I'm going to say that that the senator tree in inches is 1,416 inches, right? And then I can compare that to the bonsai tree, which we know is over here 15 inches. Okay, so they ask us specifically to start with the bonsai tree and to compare that to the senator tree. So I could do that in two forms. I could either say that it is 15 over 1416, which would be the fraction version of writing our ratio, or I could write it just as 15 to 1416. Right? And again, if we might be able to do some reducing, but what we really care about is that this is how we're setting up our comparisons of the small tree, the bonsai tree, with the large tree, which is our senator tree, in the order that they asked us to do it. Okay, so we can take this idea of ratios and we can expand on it, and they can tell us the ratio, and they can tell us the total number that we want, and we can kind of work our way backwards and figure out how many of the quantities that we would like in order to keep this ratio. So here's what they're telling us in this problem. A school band is trying to sell flowers, and they have two types of flowers. They plan on buying 120 flowers, and when they sold them in a ratio so that the number of tulips over the number of daffodils was 2 to 3. Right? So here's what we know. Okay, if our ratio is 2 to 3, we're kind of saying that I sold tulips, okay, and I sold daffodils, okay, okay. And when I added together the number of tulips plus the number of daffodils, they're telling me that the total was 120. Okay, but here's what we know a little bit more specifically, is that for tulips, that the number of tulips that we sold was some multiple of 2. So it's 2 times something. And the number of daffodils was 3. times something, right? It's not necessarily 3, but maybe it was 3 or 6 or 9 or 12. It was some multiple of 3. And that when I added together those values, I got 120, right? Because they told us that daffodils was a multiple of 3 and that tulips was a multiple of 2. The problem is we don't know exactly what value we're using in order to increase 2 and increase 3, but we know that it's the same value. So for example, maybe I multiplied this by 5, and maybe I multiplied this by 5. So if I check that and multiply this by 5, I get a 10, and if I multiply this by 5, I get a 15. Well, if I add together 10 plus 15, I don't get 120, so 5 was not the right value. So the issue is we don't know how much we scaled up 2 and 3. We know that it got scaled up in some way, we just don't know what that value is, right? So what we're going to do is use algebra, and what we know is that if we don't know something, we use a variable. We know that we're going to do 2 times some number and 3 times that same number, and when I do that, I should get 120. So this is a nice, simple algebra problem to solve. 5x is equal to 120, right? And if you multiply both or divide both sides by 5, 120 divided by 5 is 24. So what I know is that that value that I wanted to scale each of these up by, I wanted to make them 24 times larger than 2 and 24 times larger than 3. So to answer their questions, how many pots of each will we have? Well, 2 times our scaling up number 24 would be 48 tulip pots. Maybe tell this right, tulips. Okay, and if I do 3 times 24, it looks like I get 68. I'm sorry, 72, right? I can multiply, so we'll say 72. Okay, get my pen back. 72 daffodil pots. Okay. So if you notice, when I add together 48 and 72, I do get 120. 48 is a multiple of 2, 72 is a multiple of 3, which these are in a ratio of 2 to 3. If I set up this fraction, right, 48 over 72, and I reduce that, I am going to get still in a ratio of 2 to 3, right? So this is an example of using ratios to split up a quantity like 120, a total, into a specific sets of quantities, in this case 2 to 3, right? So we can do this with what's called an extended ratio, and the basic idea here is that we can compare more than just 2 things. Maybe I wanted to compare, in this particular example, 3 sides of a triangle. And so when I do this thing called an extended ratio, I can make this 3 parts, or I can make it 4 parts, or 5, or however many I want. Within this like little a to b to c ratio, there's actually 3 different comparisons. I'm comparing a to b, I'm comparing B to C, and I'm comparing A to C, all in the same problem, but we kind of made it a little bit more compact and easier. Instead of having 3 parts, we only have 1, right? So what we're going to do here is we're going to say, all right, 3 to 5 to 6, the perimeter is 98. So we're going to do the same thing that we did in the last problem, and we're going to say 3 and 5 and 6 are my quantities, and that needs to add up to 98. If I'm adding together 3 sides of a triangle, perimeter is just their sum. But again, I need to scale them up by some factor. So in this case, I'm going to say there's some number that I'm going to multiply 3 and 5 and 6 by, that when I add them up, I get 98. So it's not necessarily 3 and 5 and 6. It's a multiple of 3, a multiple of 5, and a multiple of 6. So again, if I take a look at this, I see 8 and 6 is 14. So that's 14x is equal to 98, right? And then we need to figure out, when we do 98 divided by 14, that we get that this is 7, right? So we're saying this missing quantity is 7. And so what that means is that instead of this being, it's not 3 inches, that doesn't make sense, but 3 times 7, 21 inches, 5 times 7 is 35 inches, 6 times 7 is 42 inches. If you add together 21 plus 35 plus 42, that is 98 for the perimeter, right? And these are now in a ratio of 3 to 5, of 5 to 6, and of 3 to 6, right? So these are kind of staying in that ratio. So to answer the question, what is the length of the longest side? It looks like I have a length of 42 inches for my longest side, right? So that is the similar concept, but we're doing something called an extended ratio when we do that.